Hey everybody, I'm Micah and my presentation is about aerogel. What aerogel is, to simply put it, is a very light and translucent material that has some remarkable properties. In this presentation I'll elaborate on exactly what aerogel is, its composition, how it's made, its properties, and its real-world applications. Alright, so we're going to talk about what an aerogel is, and what it's made of, and what it looks like. And to do that, we first need to define what a gel is. The scientific way of putting it is to say that it is a colloidal system that consists of a network of interconnected nano-sized particles spanning a liquid medium. A more comprehensive way to put it is that it is a porous structure filled with a liquid. Now what an aerogel is basically what is left behind when you take out that liquid. All that's left is a solid porous structure as visualized on the right by my model made in Blender. Now yes, the generality of the description implies that aerogels can be comprised of a number of different substances, such as silica, carbon, metal oxides, polymers, or even proteins. For example, Jello. It's a gel in which the solid component is primarily gelatin, a protein, and it is suspended in fruit juice as a liquid medium. You could hypothetically make an aerogel comprised of gelatin. Okay, so the most widely known form is probably silica aerogel, silicon dioxide, and that will be what I primarily reference from this point on. In this next slide, we'll talk about the process of making aerogel. Now, referring back to how I described aerogel as a structure left behind by removing the liquid component, the intuitive answer to how is through drying. But it's not exactly that simple. The problem with drying, as we all understand it, is that there are forces associated with the evaporation of liquid called capillary forces. This can cause the delicate structure to collapse. What you're left with is something called zero gel, a much denser, smaller material, which is not what this presentation is about. To make aerogel, what you want to do is to avoid evaporation altogether, and the way to do that is through a process called supercritical drying, or critical point drying. To sum up the steps, let's take silica and turn it into an aerogel. In preparing a gel, the silica is mixed with an organic solvent such as alcohol or acetone, and the gel is placed into a pressurized chamber where it is submerged into liquid CO2, in which the organic solvent in the gel is replaced by this CO2. The reason for doing so is that it's much safer this way than to use the original organic solvent. This part of the process can take a long time, sometimes days or weeks. Next, the higher temperatures and pressures are introduced in the chamber in order to bring the CO2 past its critical point into a supercritical fluid. Here, there is no distinction between liquid and gas, no evaporation, and thus, no forces to damage the structure. Finally, pressure is gradually released until all the CO2 goes from supercritical to gaseous, and what is left behind is the blue substance that is aerogel. Now we'll move on to what makes aerogel so interesting, its properties. Perhaps the most striking feature of silica aerogel is its sci-fi-like blue translucent color. Fun fact is that its color is due to something called Rayleigh scattering, the same physical phenomena that causes the blue color of the sky. This isn't the only fun fact. Every property that is presented here, I think, is of similar level of interest. Like I mentioned at the very beginning, it is extremely light. Light enough to sit on top of a flower without crushing it. See the bottom right? It's not a flower, but you get the idea. With it being over 99.9% air by volume, its density is roughly 0.02 grams per cubic centimeter. To put this into perspective, the density of styrofoam is 0.15 grams per cubic centimeter, meaning that it is about 7.5 times lighter than styrofoam. It's also an incredible heat insulator, one of the most effective insulators in existence actually, being able to withstand a direct flame without getting hot to the touch. Its thermal conductivity is about 0.02 watts per meter Kelvin. Fiberglass, a common heat insulator used in houses, has thermal conductivity of 0.3 watts per meter Kelvin, which means it conducts 15 times that of silica aerogel. The key to this insulating property lies within the structure of aerogel. The pores in aerogel, on average, are at the nanometer scale, which means that the movement of air, which air by the way already has a very low heat conductivity, is reduced to where convection heat transfer within the aerogel is effectively null. This isn't the only property derived from its porosity. Another cool thing about it is that its surface area is enormous. A sugar cube sized piece can have a surface area comparable to that of a football field. To put this into numbers, it has a surface area of up to 1,000 square meters per gram. The benefits of this I'll get into later. Finally, some interesting facts I can mention is that relatively it's pretty strong, able to support thousands of times its own weight, which probably doesn't mean much given that it's so light. Also, it's hydrophobic, which I'll talk about in the next slide too. Alright, so let's delve into how these properties have been put to use. Its most useful property is possibly its insulative ability. For example, NASA uses aerogel in order to keep rocket fuel at cryogenic temperatures. And other areas this property has been useful is in subsea systems, oil refineries, industrial buildings, homes, refrigerators, and even clothing. For example, jackets, or this shoe insert to keep your feet warm in the snow. NASA also created the first practical flexible aerogel blanket in the 90s. Another thing that goes hand in hand with this insulative ability is its hydrophobia. This property would effectively reduce the amount of water damage on these structures or the parts inside. Now onto its surface area. One feature about having such a great surface area dispersed throughout many tiny pores is that liquid loves to hold on to it. In fact, this property is exactly what made it a gel in the first place. If you wanted, you could turn aerogel back into regular gel by letting it reabsorb the solvent used to make it originally. What this property is good for is basically being a super sponge and absorbing any unwanted substances like oil spills or filtering chemicals. High surface area also means more active sites for catalytic reactions. For example, graphene aerogel, which is made of carbon, is used in air filters to filter out air pollutants. All in all, these properties have endless potential that is boosted by the versatility brought by its insanely light weight. Alright. Okay everybody, that is about what I have for this presentation. Thank you for listening.